Doesn't matter what I did, everything was successful. Then the worms come, eat the organism and turn it into a protein. It's just this humus. It smells so beautiful. If compost is called black gold, this is black diamond.
I think you mentioned about more than 200,000 tons. I think you also had the goal to go up to 500,000. This is massive. Can you tell us how many worms were working for you?
Because the next year we're on the next paddock. We are rotating like in a crop rotation. This is the advantage we can do. You would say this takes a lot of land. Actually, it doesn't. So we pay a lease to the farmer, so the farmer's not losing any money. Let's say between 1,000 and 2,000 New Zealand dollar per hectare a year. The farmer remains with 2 millimeter, 5 millimeter of vermicast, which is, again, the same money on top. So they don't have to pay for the soil conditioner. We are growing earthworms, so they have additional earthworms. Then they have the vermicast on their farm. If they want to spread more on their farm, they don't have any transportation costs, so they can utilize it on site. Now we have a new concept. We not have a centralized mixing area, and we are serving the farms surrounding us. So we're actually working with all the farmers, and we make sure every farmer gets sufficient vermicast in return for leasing their land for the revenue. That's how we integrate it in the farming. It's invisible, it's integrated. You have no big thermal composting plant which smells sometimes. You don't have these fungi, these domes, looking sometimes like, let's say, big investment, $30,000 for an anaerobic digester, which is sitting there for 30 years plus. And that's the beauty. Or we can say a disadvantage, because if you want to have someone supporting you and they want to show something to the people, let's say in government, you want to show things, but there's nothing you can see. But they're open-minded. They can see that we need to find solutions, and you can't just say, well, there is no formula, there's no template. You can't tick the box vermicomposting because it's new. So they're very innovative. And in the last couple of years, we can see there's a shift, there's some momentum. Farmers are contacting us. Can you run a worm farm at my site, please? How do we do this? Do we have some ways for in the region so we can set up a worm farm? This is why we believe, or we are convinced, we can double our capacity the next year. So we're employing more people, environmental managers, on-site managers, more staff. We do a lot of training on site, so we are ready to roll this out, ideally New Zealand-wide. And this is a game changer, because in worm farming, I can't force the worms to eat it. In the laboratory, I can put it into a jar, into a bucket, put the worms in, put a lid on, make sure there are a few holes for air and so on. So I can force the worms. But in nature, if I do it commercially, I can't. The worms need to join the party or they're gone. They say, bye-bye, Michael, and I'm not in business. They all have a brain. They're feeding around the plastic. You can do vermicomposting everywhere where you find worms, earthworms on this planet. So if they are native earthworms, the environment for these species is okay. You want to have it on Antarctica. I think you don't have any worms in Siberia, I'm aware of. So this is where you have your limitations. You won't have any worms in a desert either. I encourage every household, every single person, every school, kindergarten, your office, to start to have their own worm farm. First of all, it's fun. You find a lot of worm farms you can buy online in garden centers on our German website. You can find, it doesn't matter which type of worm farm you're actually buying. Get started with a cheap one, see what it does, how it works for you. And it's a good education purpose as well, because if you have it at kindergarten and schools, you can train the next generation and make them aware of organic resources, that it's not a waste. It's a food for earthworms. You can have a worm pandemic in your worm farm. Unless you reach a maximum capacity, then they stop breeding actually, so it's not overflowing. Converting this organic waste, organic resources, and putting it back into the soil where it can actually do its job and feeding the organism and keeping our soils alive at a higher level and be there for the next generation.
Welcome to Meirer Talks Trash. What trash is on the agenda today?
Hello, Michael, and hello out there in the world, and it's nice actually talking to you after a while. I think today we're talking about a 600 million years old technology, which is embedded in a 5 centimeter long tube. This tube is called an earthworm.
Sounds very promising. So tell us a little bit more about you. You mentioned your name, Michael as well. But what are you doing? What is your background?
Yeah, my name is Michael Quintern. I've got a German background, so my accent, if you wonder, is German. But I'm living in New Zealand for 15 years now. So came here in 2006. I studied agriculture in University of Göttingen and did my PhD in soil science and plant nutrition at the university in Kassel in Witzenhausen, working on land application and utilization of organic resources. Some would call it waste. I don't like organic waste. There is no organic waste. It's a resource. And working on how to apply organic resources or integrate it in farm management so we get most benefit out of these resources while mitigating all negative effects. I was working at University of Kassel probably 12 years almost, and then I got a job opportunity from a Crown Research Institute at Scion here in New Zealand to become the technical manager of the New Zealand Land Treatment Collective, as well as looking at opportunities and alternatives and technologies to take organic waste from large pulp and paper mills and put these back into soils. This was back in 2006, and the first initial years were so successful that I had to start my own company 14 years ago in March 2007. So we just celebrated the 14th anniversary. Okay. Since then, we have grown in our worm farming business, or vermicomposting is the technical term. Since then, and grown steadily.
Sounds great, and congratulations already to your 14 successful years. Maybe we will talk a little bit about the ups and downs. But let me go back to 2006. When you said that you had this project to deal with paper mill waste, how did you came up with worm composting or vermicomposting? We have to talk about the right term in a minute. But how did it come that you've chosen this technology?
So when I first visited a pulp and paper mill, I mean, back in Germany, you have some of those. Most is about recycling paper. So here, these are large, very large factories. So they take wood chips, take trees from plantation. So it's like a carrot, just the carrot grows 25 years, and then they harvest this tree, planting new trees immediately, and then these trees are turned into wood chips and they're cooked. So the hemicellulose fiber of these trees are turned into pulp, and pulp is turned into cardboard or paper. But some of these hemicellulose fiber is lost in the system, and they take it out of the wastewater stream and separate it. And there are 5 large pulp and paper mills in the central North Island here of New Zealand, altogether producing around about 250,000 tons of these fibers. And all these fibers have either been burned or landfilled and pushed into valley.
Is this also the state of the art outside of New Zealand, in the world in total?
I think it's very common what I have read recently in the papers, so what I'm able to follow. So you have this fiber, and it looks really like wet cardboard, and it's basically carbon. In soil science or in organic waste management, we're often looking at carbon, nitrogen, phosphate, and the nutrients. And we have to make sure that actually this is digestible either by bacteria, and we talk about earthworms a lot today, or fungi, basically. These are the 3 main organism in the soil breaking down this organic matter or processing it. But you need to have a good balance. So you need to have, we call it a CN ratio, carbon-nitrogen ratio. It's a bit more than that. It's also phosphate and all the other nutrients. And the pulp mill solids, these fibers, they just contain carbon. They have a CN ratio, depending on the wastewater treatment plant, between 50 and 200. And it's almost impossible to land apply it directly because it will absorb a lot of nitrogen in the soil, which in some areas would be beneficial, but mostly it's not because you can't grow any plants out of this. So we needed to find a technology, and the state of the art back in those days, 15 years ago, was thermal composting. So you would add a lot of nitrogen fertilizer, usually urea or any of these affordable mineral fertilizer. You have to blend it, mix it, and then you have to turn it around. And this was the state of the art. But we looked at how can we implement it for 200,000 tons? And it's too expensive.
Wow.
You can't. It's just too expensive. You can have a small portion as peat replacement for potting mixes, but New Zealand has a population of close to 5 million now, of the size of former East Germany, just to give you a comparison. So like Berlin on West Germany, so to speak. So this was not possible. And my group manager at this research institute at Sion, he is from India, Gunnar Magazine. And Gunnar was familiar with worm farming. He heard about this and he said, Michael, you need to look at this worm farming. And I said, what's worm farming? Oh, you use earthworms to break it down. And I said, really? So I was searching on the internet, and then I was lucky there was a small semi-commercial worm farm around the corner, meaning 100 kilometers away from us. And I went down there and I saw this, the first time I saw a small, medium-sized worm farm, and I was able to put my hands into these, we call it windrows, into the worm farm, and holding, which is called Vermicompost, the worm casting. In German it's called Wurmlosung, and full hands of those. As a soil scientist by training, I've seen worm casting, which is a mix of organic matter and soil particles, but here it was a pure humus worm casting. And I thought, wow, if compost is called black gold, this is black diamond. So I thought, if I can produce this commercially, this is big business. Yeah, and this is where it started. So I had to do some trials and then in small pots in the laboratory. I was very lucky to find someone with some farmland, and we did some trials in his backyard, and they were successful instantly. And so this is how it all started.
Great.
And this is how I get involved into worm farming. And I haven't learned anything about this at university. I've never seen a worm farm before. I just saw the end product and did some trials and was convinced this is a technology we all have not been aware of, as we should have been. There are what we call developing countries, and I think they are much more developed than we are in this area, who are doing this for hundreds of years. And we haven't. We just went for technology, technology, technology. And the technology is actually in this 5 centimeter long tube, just like this pencil here, just this much. And one of these scientists told me, if we would take all the 300 scientists from Sion at those days and we put them all together in 1 year, give them all the funding, we would struggle to come up with a technology which will be almost equal to this one. So I decided, okay, I don't want to beat nature, I want to work with nature, and let's see how this works out. Yeah, and that's what we're talking today.
You mentioned a lot of things. I have to maybe ask you a little bit and go a little bit more into detail. First of all, you mentioned that you haven't heard about that or learned about that on university. Me neither. I've studied environmental protection, waste management, and you almost don't hear anything about that. Yeah, just technology. Maybe because also the manufacturer of the thermal composting companies, of the AD anaerobic digestion plant companies, and so on, they are supporting the universities, and therefore they want that this is taught to the students, and not this very innovative technology, which is very old but still state of the art. Great technology. I'm really looking forward to get more into detail now. And you mentioned already a couple of different terms. I had worm farming, I had worm composting, I have heard vermicosting, vermicomposting, and I also did some research or some search on Google, and I found about 2.75 million results for worm composting, 0.9 million results for vermicomposting, and so on. Could you explain what maybe the scientific term of this treatment method is, and what the most common term is, if there is a difference?
The correct terminology from a scientific point of view, and if you want to read a lot of papers on this, and there are thousands out there with vermicomposting. It's a technical term, vermicomposting, spelled with a V, not with a W. It's not worm composting, because we are not composting worms like green waste composting or farm menu composting. We are not composting worms. Actually, we are not composting. It's a fermentation, a breakdown of organic matter with the help of worms. And it's not only the worms, it's actually all the microorganisms in this environment, into this microsphere, if you like. So there are fungi, there are bacteria, protozoas, there are so many microorganisms. Actually, all these beneficial microorganisms living in the topsoil for millions of years. And a lot of these are living inside the guts of the worms, so in the stomach of the worms. But we'll talk about this later, how this all works. Another term what a lot of people use is worm farming. And worm farming is probably a more domestic term. If you want to do it at home, smaller scale, it's worm farming. And it combines both things. Vermicomposting is more focusing on organic waste management, processing the organic resources. And then we have the terminology vermiculture, which is more about breeding worms. So it's similar when you're growing these black soldier flies, where you're concentrating on producing a protein. So vermiculture is concentrating on producing earthworms for a lot of purposes. For fishing, you find literally dozens of worm farms in the Netherlands and Poland, and some in Germany actually, breeding earthworms for fishing. We can't do this in New Zealand. It's forbidden to use worms as a bait for fishing, but that's a different story. But you can use these worm tissue, the earthworms, or the worm meals. If you harvest these worms, kill them, dry them, ground them, you get a protein source which has a higher value than fish meal. And probably, I don't have any comparison to insect meal. Probably depends on the species as well. But it's very highly looked after. And especially countries like Vietnam, China, Asian countries, and India, they use a lot of these products in feeding fish, chicken, even for human consumption. It's high quality. So these are the two terms, vermiculture and vermicomposting, and worm farming. In Germany, I would use the term Vererdung mit Regenwürmern. So it's kind of stepping away from composting, because composting is actually a thermal process reaching high temperature, whereas vermicomposting is a low temperature process. So generally you don't create any heat, because worms wouldn't survive the heat, and you want the worms to live in there.
Maybe later, I hope not to forget to ask you about the legal perspective, because you mentioned it's not a thermal process, so maybe the sanitation, hygienization may be a topic then. But I want to continue with what you said, that you are producing soil, black soil, the highest quality soil, maybe a good humus. Could you maybe explain maybe the difference between a loamy soil, a clay soil, a black soil, a humus soil for us as non-experts? You've done a great TED Talk. Congratulations to that. And there you showed two pictures of two different types of soils. Maybe I will show these two pictures. I will cut them into the video. But could you a little bit explain the difference between all these types of soil, please?
In soil sciences, we don't talk just soil. So we have soils, plural, because all the soils are different, and different by what kind of mineral or stone they are just built from, and over time, and what factors like human activity has created those soils. And basically, we need to look at the mineral part first, and we usually have sand, silt, and clay. So sand is very coarse, you know it from the beach and from deserts, 2 millimeter and smaller. And middle part is silt. Often it's kind of floury, feels like flour. So less silt soils in Central Europe, and a lot of these soils in the US and especially China. And then we have the clay particles, which are 2 micron, and they are so small they fit into your finger in the rills in here of your fingerprint. And this is what we call the texture. So you have a clay soil, which is predominantly clay minerals. You have a sandy soil, just sand, and then you have a loamy soil, which ideally have a third of sand, a third of silt, and a third of clay, which are the most fertile soils. Important for the soil is how much water they can hold, or we call it soil functions. So a soil has different functions: growing food, having an environment for animals to live in and above, filtering our water, holding water, and many, many more. And this is done through the mineral parts. Some of them, clay, can hold a lot of water, but the plants can access it. Sand can't hold a lot of water, but most of the water the plants can access. And loam is in the middle, can hold a lot of water, and a lot of water is plant available. The second part in a soil are the organism, the organic matter. You don't have a soil without the biosphere. So we have the lithosphere, it's the middle part. We have the biosphere. We need to have an atmosphere, so we need to have air and carbon dioxide and oxygen. And we have the hydrosphere, water in the soil. If any of those is missing, we're not talking about a soil here. So we need organic matter. Without organic matter, there is no soil. And the organic matter is, of course, living animals and plants and microorganisms, but it's also dead plants, dead animals, dead microorganisms, which are decomposing, and there's the word composting, composing, or decaying in the soil. And they turn slowly. We call this organic matter at some stage. So a fallen tree is already organic matter above the soil. Dead roots in the soil is organic matter, but their function is limited. As well, as soon as microorganisms, fungi, bacteria, and earthworms and others are decomposing these organic matter and mixing it into the soil with the mineral parts, we develop a humus. Humus is, as my soil professor, Professor Meirer said, it's, ladies and gentlemen, we're looking at the black part in the soil, the black box. And in those days, there was not much known about organic matter in the soil, humus. We all know it's important, but it's still very difficult to do tests and analysis and compare this organic matter. And this is the black stuff in the soil, actually. It's holding the moisture, it's feeding organisms, it's the habitat for the soil organism, it's feeding the plants, and much, much more. So to improve soil fertility and soil functions, I'm focusing on getting organic matter up. If the organic matter is higher and we have a healthy soil life, we have fertile soils. And these soils can take care of themselves a lot. They don't need a lot of support in regards to pest control or the others. Unfortunately, a lot of intensive farming management practices are actually very hard on the organic matter, meaning we are not taking care of the organic matter and the soil organism in the soil. Part is we try to harvest as much from our paddocks as possible. So any fiber we can harvest for any purposes, we're taking off the land. But the organism in the soil, they need to feed on something. As we need a sandwich, a salad, some nice food, they need organic matter. They need carbon and nutrients. If we don't feed them, they disappear. If they disappear, we have less organic matter in the soil. And then out of a sudden, the whole soil function is decaying, is declining. So that's a major problem. And the idea is, on the opposite, you remember these pulp and paper mills. We are producing 200,000 tons of these in the Central North Island. And I think there was a study that we're generating 2 million tons of organic resources, organic waste on these two islands. And most of this has been landfilled in the past, and a lot of still is landfilled. So New Zealand has hardly any incinerators, so we are not burning any waste. And in countries like Central Europe, a lot of organic waste is incinerated because we have so much, we don't know what to do with it. At the same time, our soils are losing organic matter, humus. So the logical approach would be converting this organic waste, organic resources, and putting it back into the soil where it can actually do its job and feeding the organism and keeping our soils alive at a higher level and be there for the next generation. Unfortunately, we can't take pulp mill solids and some other waste, putting it straight onto the soil. It wouldn't work. We would overload the soils. We would probably do more damage than we would do any good, because as we always do, we often do, we're just doing too much. So the process here of, let's say, thermal composting and vermicomposting is processing, stabilizing, fermenting these organic resources, organic waste, to put it into a product which is safe to handle for humans, safe for microorganisms in the soil, and safe for the environment where we're applying it on farmland, horticulture land, in the forest, as a potting mix for our gardens, even in small gardens at schools, kindergartens. We want to make sure these products are safe and they are almost free of any contaminations like plastics or heavy metals.
Michael, I'm sorry, I have to interrupt you because there are so many interesting things we have to add a question. First thing was, you said that we should try to, I think we are all aligned, to burn less organic waste, to give it back to the earth, to the soil. Totally agree, but I think very important to mention is here, we have to start very early. We have to separate the waste at source. Then we are able to do it. In Europe, you mentioned that parts of it is burned, I think mostly with the residual waste. If organics are in residual waste, they're more or less lost. I think we are both aligned here. So I think there it's very important to have a separate collection, and if we have it, then we have at least all options. And the other thing you mentioned, you talked about the organics in the soil, and I think in your TED talk you also said that muck or organisms need muck to be able to digest straw. Can you explain that a little bit? How the biosphere or biological process here is working, why they need it, and how this is going?
Yeah, it takes us back to vermicomposting, actually. So we have these carbon-rich organic resources, which is this paper waste, if you like, cardboard, pulp and solids. And the similar is straw. So straw from our grains, cereals, is basically carbon. And the microorganism, it takes them a long time to break down this carbon because they need the other nutrients, nitrogen and phosphate I mentioned earlier. And at the same time, we are generating a lot of organic waste, which is rich in nitrogen and phosphate, but doesn't have any carbon. So what we need, and in nature it's very well balanced because you have the grass is growing and you have cattle and horses feeding on it in nature, and they are pooping, they are just leaving their manure behind. So you have muck, manure, and you have your straw, and the microorganism can mix it. So if we separate this in our industrial world, so we have the pulp mill and the paper waste and everything, and we have biosolids, sewage sludge, and we have sludges from wastewater treatment plants, from milk factories and food processing plants and an abattoir, and we have also the food. Well, on one hand we have the carbon, on the other hand we have the nitrogen, the nutrients. We need both. And what farmers often do if they have just grain, they're just putting in mineral fertilizer to balance it, which is called a priming nitrogen source, to break down the straw to get it rotten. Otherwise, it just accumulates in the soil, while a lot of farmers burning it, unfortunately. So that's what we do in vermicomposting.
And in New Zealand, I think you managed it very well to mix this carbon-rich, not waste, resources. I really like your way of looking at this. Your carbon-rich resources, or in German we have this Sekundärrohstoffe oder so secondary resources. I don't know if you can directly translate that. So carbon-rich, and also you found some protein-rich resources from I think the milk industry. You already mentioned it. So can you give us a little bit? Can you take us into how you managed to find the right mixture for your worm farm, for your company, and also how you got to these huge amounts of resources you treated? I think you mentioned about more than 200,000 tons. I think you also had to go up to 500,000. Could you tell us a little bit where you are at the moment? And because this is, when we're talking about 100,000, 200,000 tons a year, this is massive. Can you tell us how many worms were working for you? Did you estimate that, or did you do your calculations here?
Yeah. So I tried to take it step by step. So I had the carbon, so I need to find the nitrogen. And from my background in Germany, I was looking at, there's a lot of biosolids, sewage sludge. So, and all this is landfill as well. So this was an easy approach, easy to mix. Other waste streams I started instantly were, we call it DEF, dissolved air flotation. It's the cream, the fat in a milk plant. Actually, it's like, cream. It's very fatty, full of nitrogen, smells horrible, and you can apply it on the farmland, but it does more harm to the soil than any good. So I mixed these and lake weeds. So there are a lot of weeds growing in the lakes and rivers, and they need to be extracted. And so another source of nitrogen. So I was combining those, and it doesn't matter what I did, everything was successful. If you got the ratio right, some ratios were a bit strange. As a scientist, you do a control, 100% biosolids, the worms didn't touch it. The other 100% pulpal solids as another control, the worms didn't touch it. But in between, as soon as you got a reasonable ratio, the worms loved it. Sometimes a bit faster, sometimes a bit slower. At the end, it didn't matter because the worms just ate it. That's important, because in worm farming, I can't force the worms to eat it. In the laboratory, I can put it into a jar, into a bucket, put the worms in, put a lid on, make sure there are a few holes for air and so on. So I can force the worms. But in nature, if I do it commercially, I can't. The worms need to join the party or they're gone. They say, bye-bye, Michael, and I'm not in business. And this is how it started. And I instantly could see, yeah, that's working. And then it all comes back to the economics. How are we going to do this? So the worm can't eat paper. They don't have any teeth. So some of these species are called tiger worms. It's because they have those stripes, but they don't have teeth. They can't chew. They are more like a bird. So they have a gizzard, they swallow it, and the stomach is grinding it with a muscle. So it needs to be very small so they can eat it. So wood chips, sawdust, we can't feed the worms. They can't swallow it. It needs to be paper-based or slurry, wet material, which is difficult to vermicomposting because the moisture content is too high, but it's ideal for worm farming, vermicomposting. So the worms are swallowing it, they're grinding it down, they are kind of killing the bad guys like E. coli, salmonella, all these pathogens we find in biosolids, in our sewage sludge and in chicken manure and elsewhere. Then they're extracting a lot of nutrients of the nitrogen phosphate, building up the organic matter. They're growing very fast. then they are reducing the volume. So from 100%, we're losing 80% of the volume. So only 20% remains in worm casting, worm poo, and it's a kind of a micro pellet, like these goat droplets, and this is released. So that's why it's happening with different.
Yeah, I want to interrupt you here. You said you lose 80%, and we as scientists know the math balance, you lose nothing. But what are you losing? Is this water, and where is it going?
Let's call it waste management. So waste management, usually collecting and dumping it somewhere. That's what I call waste management. We're in the area where we are processing it. So, and their volumes matter because a landfill is based on volumes. So most of this sludge is water. We agree it's 80% water, 20% are solids, give or take. And 20, remember that 20 is a very important number in vermicomposting. So 20% solids is ideal, give or take. So most of this is water. The worm casting at the end may have something about 40% solid. So you can imagine some moisture is lost, taken out of the equation. Then there's a lot of carbon, and the worms are breathing. So they need oxygen. So it's an aerobic process, not an anaerobic. So we don't produce methane. It's just CO2. When the microorganisms are living in the soil, releasing CO2. But it's a normal process because it's organic matter, carbon. We took from the atmosphere, we're giving it back. It's not fossil carbon. And then we are building organic matter, organic matter if you like. We're building microorganism, fungi, and earthworm organism, tissue, volume. So if the worms living in a perfect environment, we have 2, sometimes 3,000 worms per square meter in a worm farm. In a good soil, you should have 300 worms per square meter. So we have 10 times as many worms in a worm farm. So the process is 10 times faster than on the soil. Just imagine this. So you're speeding this up, really. And the worms double in mass every 2 to 3 months. Not in winter, but from spring to autumn. So they double. And you need a lot. If you're growing pigs and you want to double a pig within 3 months, you need a lot of nutrients for this animal. So all these nutrients are extracted from the organic matter. And there are only few technologies where this is happening. It's the similar with growing black soldier flies, for example. But you don't have this in thermal composting. You're not extracting anything. You're just burning some carbon, oxidation. In anaerobic digestion, only a little carbon is turned into CO2 and CH4, methane, biogas. All the rest remains in the product. That's why, as a rule of thumb, in thermal composting, we lose 1/3 in volume. So we have 2/3 we have to take away and find an end user. Vermicomposting, let's say, 2/3 are lost or are transformed in the process, and 1/3 need to be transported. In anaerobic digestion, it's the same. Sometimes we increase the volume by adding water to it. So we have what we're putting in, we have to bring out. So that's a big difference. I'm not very familiar with black soldier flies, but it's probably similar to worm farming.
And what was the maximum your company, your plant treated per year? 100,000, 200,000 tons, or?
We started slowly. So I was collecting worms, like 20 bucketful of worms around an old waste pond, one of these dewatering ponds. And a worm can eat up to his body weight per day. So I have to eat a lot of ice cream a day to compete with a worm. I can't. Which means if I have 1 ton of waste per day, I need 1 ton of worms on the worm farm, a minimum, probably 2 tons of worms. So we were growing steadily over time. At the moment, we are processing close to 200,000 tons per day. We have a capacity of more than 250,000 tons we are allowed to process on our worm farms. And we are considering to double this within the next, let's say, 12 months. So we want to get beyond 500,000 tons of organic waste, which is probably 1/4 of all organic waste in New Zealand, according to this reference I mentioned earlier, going through a worm farm.
This is very, very impressive. But I'm just wondering, When you mentioned these enormous amounts, when I did some search on Google, on Wikipedia, they're saying vermicomposting is very popular, or you find vermicomposting in huge plants in India, in Italy, in Canada, in Malaysia, in the Philippines. But New Zealand wasn't there. So are they even treating more, or did they just forget you?
It's a matter of scale. So there are some very large worm farms in the US, and there are some large worm farm in India I'm aware of. But India has thousands of worm farms, but they're all very small in comparison to us. They are probably big in the circumstances and in the context in India. Scale matters. Scale matters in a way. First of all, we can combine organic waste streams, byproducts, which we call Sekundärrohstoffe. Sometimes I think it's actually the primary resource, and maybe the paper is a byproduct, but it's on the same level, and I don't want to differentiate too much. So the other product from these industries, we need to process, and to make it cost efficient, scale matters. And this was the challenge. How can I upscale it so I can take 50,000 tons from a pulp and paper mill, plus adding, let's say, another 50,000 tons from other resources? So the largest worm farm, we have a capacity of 149,000 tons we can operate. And how can I make it safe to the environment? And this was a challenge. So obviously it's getting it to a place is easy. You put it on the truck, and if it was trucked to a landfill 100 kilometer, you can truck it hopefully less than 100 kilometer to a worm farm. So that's easy. You put it on the truck, and instead of taking it to the landfill, you take it to the worm farm. Here, it's a bit of a logistic. We have to bring in these two waste streams. Let's concentrate on two, biosolids and pulp mill solids, and to mix it in the right ratio. So we did some trials to make sure it's, first of all, the worms love it. Second, we can generate a product which is safe to the environment. So it needs to be less in heavy metals. We have to reduce pathogens, and it's still rich in carbon and nitrogen phosphate, so the farmers want to take it on the farmland. And the third is, when operating on the farm, we do not want to pollute the underlying soil, because we are operating on the soil. There's no concrete. There's no plastic lining, there's no roof on top, there's no irrigation. We just work with nature and looking what the worms need and how it needs to be done to be safe. Once we met all these, we can upscale it. That was a challenge. And now we have 7 worm farms. We're just working on another one with this capacity of 70,000 tons per year. And hopefully we get it up and running by June.
And you're not only operating, well, there is MyNoke New Zealand, but you're also working on establishing, I think, MyNoke Europe. But maybe due to the pandemic, you're not able to commute between New Zealand and Europe at the moment. But what are your plans in Europe, and where are you doing it, and what are you doing here? Or if you want to talk about that, maybe if it's not confidential.
Beside MyNoke Limited, which is a company in New Zealand, we do have MyNoke GmbH in Germany and MyNoke BV, which is in the Netherlands. The reason is I was contacted by scientists, not just by you as well, from these several conferences I was presenting in Europe, from the Netherlands, and looking at their Meirer, which is all the organic matter harvesting from their canals and ditches. Well, we know there are some of the countries below sea level, and they have to make sure the water's getting out of the country. So the canals is essential, and they're producing 200,000 tons of this Meirer, this grass cutting out of their canals. So we did trials on vermicomposting these grass on the farm next to the canal, and it works fantastic. So you just put it on the pile, add some worms, and literally leave it behind for the worms to digest. And then, of course, you have to inoculate with worms, and then the farmer can use a vermicast and spread it out, and by doing so, he's growing the worm numbers. So it's a very smart, simple, easy approach, and the farmer can benefit from it. In Germany, I've been approached from, especially from the far north region, with all these 8,000 anaerobic digesters, and because they are struggling with the digestate, with this slurry coming out of these anaerobic digesters. And very often it's separated. So they take the slurry, which is, I think, 4% solids, which the microorganism can't process, turn into methane. So these biosolids are separated, so pressed out, or the liquid, and then this organic matter, this was 20% solids again, we were trialing and testing if the worms can eat it. And that's why we started in Europe. But now with the pandemic, we concentrate in New Zealand, and New Zealand is a safe haven. So the government is doing great. Not the government, the people are doing great here in New Zealand, and we can actually contain it. It's just in a few hotels at the airports when people are coming back to New Zealand.
But do you have your safety measures? Like, do you have to wear a face mask, or are you like before Corona, COVID?
It's recommended in public traffic, and I think it's wise to do so because that's where the highest risk of spreading it. Otherwise, it's almost normal. Yes, we are tracking using our app. Everywhere we go, we scan where we are, so we get an alert if something is happening. We had a few shutdowns for a few days, sometimes a week, or partial shutdowns, basically most of the time in Auckland, and we're supporting our Auckland people and helping them. And but at the moment, there are concerts, and you might have seen the Americans Cup sailing in Auckland, and you have seen tens thousands of people gathering without a mask. We're safe.
We're looking forward in the rest of the world, I would say, to get this normal life, hopefully as soon as possible again. But let's go back to worm farming, vermicomposting, and maybe do a little bit of comparison to the conventional composting. And I would like to go through all the important criteria, so air, time, space, water, and so on, and go through the pros and cons of both of these methods. So vermicomposting and conventional composting. Starting with the costs. What is important for the cost of such a process is maybe how many labor do you need? How many space do you need? You mentioned already how high the heap can be. If it has to be under a roof or not, well, it depends maybe on the region. But starting with the costs, where do you see a benefit, or what produces costs on both of these composting methods already? Although you already explained that vermicomposting is not a real composting, it's producing soil. Huh?
Let's compare three technologies. Vermicomposting, the way we do it in New Zealand, so there are different ways. You can actually do it indoor with high-tech machines, raised beds, and if you do a bit of searching, you find there's a lot of technology about vermicomposting. So the way we do it here in New Zealand. Second, thermal composting, and I want to compare two in there as well. And then anaerobic digestion, because these are the questions we ask a lot. How do these three technologies compare? The organic resources are collected in the same way, so there's no difference. And they should be clean, of course. So none of these technologies can handle contamination. The worm farm has some advantages we can talk about later if you want to. They need to be transported to the site. So we can have compost sites, we have anaerobic digesters and worm farms. So ideally it should be in a region. So we don't want to have a lot of traffic going on the roads. Vermicomposting and composting are aerobic, so they are working with oxygen. So there's no, if done correctly, and we're assuming everything is done to the book, they're not releasing significant numbers of methane. It's all carbon dioxide, and we are concentrating, reducing, fermenting, stabilizing the product so it's safe for the land. Anaerobic digestion, it's anaerobic, meaning without oxygen, and therefore the microorganism in there use the carbon as an energy source and producing not CO2, but C8 from the water, CH4. That's the difference. So one is aerobic, the other is anaerobic. So for the aerobic ones, we don't need to seal it. So we don't need to enclose it and make it airtight. Whereas for the anaerobic digesters, need to be airtight for two reasons. First, we want to keep the oxygen out so these bacteria can actually do their job. Second, the worst thing is if we're losing methane, it's 25 times more dangerous than CO2. So any molecule of CH4 is really dangerous. So we can't have this, and we can talk about this risk a bit later. So it's more, it costs you more to build an anaerobic digester because it needs to be sealed off. Okay, very much enclosed, controlled technology.
So the investment costs are much higher for anaerobic digestion.
The highest is in anaerobic digestion. Vermicomposting can be done in windrows in the open, and a lot of countries still do this. But in Europe, our legislation requires sealed on the floor, which I think is a very good idea, putting a roof on top. And if you are close to people living next door, like in most places in Europe, you have to seal it off and put it through the air, through an air filter. Because it's a hot process, it gets to 65 degrees, you get a lot of steam coming out of it and alcohols, what is part of the process. So the whole plant is steaming, and the steam is carried away with the air. And you can smell it. So the vermicomposting, you can smell the sweet odor, and if it's going bad, you can smell it instantly. Again, you have to make it in such a way that actually oxygen can get into this pile of organic matter, either by pushing air through or sucking it through or enclosing it. So more investment costs. In worm farming, we are mixing those waste streams, which you have to do in all the 3 ones. You have to mix it, sometimes you have to hog it, meaning shred it. And for anaerobic digestion, you have to make it sure it's very, very fine to go through the process. And wooden material and paper, it's very difficult to put into an anaerobic digester. So there are already limitations here, some limitation in composting and some in vermicomposting. So we mix it, and then we bring it out to the field. We are putting it onto the farmland, into the forest land, under trees, on the open field, and we apply it between 50 centimeters and, let's say, 80 centimeters. We're putting in some worms, and then we go away. We walk away. We are not churning it as you need to do in thermal composting. We are not pumping it around as you do in anaerobic digestion. We just leave it. The worms are doing it. The worms are moving it around. They're turning it upside down. It's called, in soil science, we call it biotubation. The organic matter is turned around by the microorganism. Here I would call it vermitubation. So the worms are actually turning it around. So we save all these costs. And then we come to harvest, so we can pick it up. We can spread it out instantly, but we do a bit of a screening first to have a nice homogeneous material, which we can use in fertilizer spreaders. Composting, you have to screen it as well. That's important. Anaerobic digestion, you have to put it into a tank wagon if you apply the slurry additives, but you have to put it in a holding tank first, and then you have to apply it. So the holding tank is another big investment. And depending on the country you're living, this can cost a lot of money.
Summarizing the cost for CAPEX, capital expenditures, there is definitely a point for vermicomposting compared to thermal composting or AD treatment, less or the lowest costs. As well for OPEX, operational expenditures, I think that if you don't have to turn the heap, if you just put the worms there and leave it, definitely the lowest costs or as well for compared to anaerobic digestion. So CAPEX, OPEX, definitely 1 point for vermicomposting. Then you mentioned Odour. I think, how does it smell on your warm heap? Is there any smell, or does it smell like wood?
First is when we receive the product. So if a truck tips off biosolids or pulp solids, this product smells like it is. So I mentioned earlier this DEF from the milk plant. It smells horrible. Biosolids, depending on the wastewater treatment plant, how they process it, some are really sweet, some don't smell at all, and some are very offensive. Pulp solid smells a bit like wet socks in a gumboot sometimes, so it's a bit more, so the reception area and where we're mixing it, that's smelly, so you don't want to have it next to anyone's place. So it needs to be 500 meters away from somewhere, ideally as isolated as possible, unless we cover it and have an air filter, but we want to avoid this. While mixing, we can all instantly see it stops smelling. And then there's a little odor, little smell when we put it into those windrows. And if you come a couple of hours later, the smell is gone. It's sitting in these windrows, and from there on, it doesn't smell at all. Then we do the harvesting, and the vermicast smells like a forest soil or a garden soil. It's just this humus. It smells so beautiful, as some people say. A good, very well done compost smells very similar. Anaerobic digestate, it smells horrible because it's full in ammonia and ammoniac. It burns your nose. We use it for cleaning windows, and that's a problem.
I totally agree, and I think concerning Odour, all technologies have the same problem. If they receive the waste or the resources from the paper mill, from the milk industry, this material, this waste, this resource has an odor. And when you mix it, of course there's an odor, and therefore maybe this has to be covered in a small building, whatever, and then I think if it's mixed, it's not so bad anymore. And therefore, in an anaerobic digestion process, more or less everything should be covered. Yeah, and in a perfect process, they are just pumping it from one tank to another, and you never smell it. But of course, the digestate, when it's applied to the land, again, you have this odor, and therefore they are just doing it before it's raining, like with the slurry.
But if you spoke about the economics, we also have to look at the disposal cost or the application cost. Disposal is for waste, application for soil conditioner or fertilizer. So you remember I talked about the worms picking up, growing fast, and they need a lot of nutrients. And these nutrients are those ones who are easy available or plant available or leachable, which can be leaching out of the process, can be lost. So the worms are picking those up, so the bacteria and the fiber actually, and this is probably the reason why it doesn't smell as much. These paper fiber or pulpman solids, they are used as cat litter. So they're absorbing the nutrients. They can hold up to 4 times the liquid. Try this with a wood chip or in thermal composting. It doesn't work. Far away from this. And they absorb it. They absorb, lock in the ammonia, which is usually the smelling part of a waste stream. And have a large surface area, so the bacteria can instantly pick up the nitrogen and some of the easy available carbon to build organic matter, microorganism. Then the worms come eat the organism and turn it into a protein. So all this nitrogen is taken out of the equation, out of the process, out of the environmental danger of the risk and the mitigation. You don't have any of these in thermal composting or anaerobic digestion. You're accumulating it. So here we can see the way we are doing it with the worms out. We are decreasing in nitrogen content. So the nitrogen content becomes less. Our nitrogen content is sometimes 0.8 up to 1.0. Good thermal composting up to 3.0.
What unit? Milligrams per...
On percentage on dry matter.
Oh, okay.
So make it really comparable. So first of all, we have got a soil conditioner, which is not releasing much nitrogen in our process, the way we do it, because we're concentrating on the carbon. We don't need another nitrogen fertilizer in New Zealand. We have a lot of nitrogen. We have excess nitrogen, too much, and the same probably in developed countries like Switzerland, Austria, Germany, Netherlands, and many, many more. So we don't need more nitrogen. We want to get it out of the system. Composting accumulates it. Anaerobic digestion converts it because they don't have a volume reduction, significant volume reduction. They actually take it from a more stable organic fraction into a mineral part, which is ammonia in a liquid form. Behaves exactly like a mineral fertilizer. And you put this liquid into a soil. And it depends on the soil, how the soil can actually handle it, and the year of when you apply it. So if it's in spring or summer, the plants are growing, can pick up the nitrogen. You can't apply it in autumn or winter, so you have at least 6 months you have to store it. And that's where the costs are. And you have to transport far more. So the less in vermicomposting, 1/3 of what you're putting in, 2/3 in thermal composting you have to bring out on trucks and spread it on farmland, and 100% as a liquid, which is more difficult to apply with liquid with the leachate, the digestate from the anaerobic digesters. Vermicast you can apply any time in the year if the soil can carry your machine, so it's not too wet. You can apply it in winter, there's no harm. Compost, almost the same, a bit more dangerous in autumn because you can have mineralization in autumn. Anaerobic digestate, only in spring and early summer. So, and this is where the limitations are, where a few more benefits coming into while vermicomposting works very well here in New Zealand. Every country is different, every situation is different, but it works pretty well here.
What you're allowed and not allowed to put on agricultural fields or mostly in the waste legislation or in the land legislation, they have the difference between do you apply it on agricultural land or on other green fields, and of course there are differences between all the countries, between maybe Europe and North New Zealand. What are you allowed to do in winter and what not, and if it's frozen, the soil is frozen or not. But we will talk about the legal aspects in a minute. But okay, we talked now about the costs to invest in the plant, to run the plant, and now you mentioned the costs or the earnings of the product, and I think we can agree that the product of vermicasting is at the highest quality. Can you give some numbers to that? So can you tell us at what price are you selling your product? Is it Vermicast in the end, or do you have several? Do you have just a solid product in the end?
It always comes back to supply and demand. So if you're looking in Central Europe and you want to buy a ton of vermicast or vermicompost, vermicast, let's explain the two products. Vermicompost is what you find in general out there, so in the literature. If you look for vermicompost, you find a lot of literature. Australia and New Zealand, we are differentiating because vermicomposting is popular here. Vermicast is pure vermicasting, and vermicompost is a mix of compost and vermicast. So there are some parts, if you have some green waste in there, which is not eaten by worms, that's vermicompost. So here in New Zealand, I use the terminology now vermicast. So that's what we are producing. Everywhere else it would be called vermicompost. So vermicompost in warm humus in Germany is costs up to 500 euros a ton if you buy it from some commercial operators, and even more because there is so little available. Australia, it's about 200 to 300 Australian dollar, which is probably about, let's say, 200 euros. I know that in some countries, Middle East, it's 200 US dollar a ton, a minimum at least. In New Zealand, because we are producing 50,000 tons of this, we can sell it for 20, 30, 40 dollars, depending on the quality per ton, New Zealand dollar. And that's about 0.6, so it's about 12 to 30 euros a ton. Compost here is sold for $60, meaning 50 euros a cubic meter.
But the numbers you just mentioned, are they for a unit of one truck or of a 20-liter bag?
Oh, we're talking bulk. So we're talking truck and trailer units. So most of our customers ordering the minimum is 30 ton. That's a truck and trailer unit here. And we have customers taking 3,000 or 4,000 tons of vermicompost.
Have you thought of packaging it and selling it in supermarkets?
If you go to our website in New Zealand, you can see we're selling it at 10 liter, 17 liter, up to a cubic meter, these bulk bags. And we're rolling out this product. We joined with some potting mix companies, and they're integrating vermicast in their potting mix. It works. Interesting market, growing market.
And if we're going back to our comparison of the three treatment options, I think we have talked about the costs, CAPEX, OPEX, and the product. We've talked about Odour. Maybe talking about time. You said that, or what is the time to treat 1 ton of waste or resources, how long do the worms need to eat it, to transform it into worm compost, and how long is the conventional thermal composting process, and how long the AD process? What do you think if you compare it?
First of all, we have a continuous flow system. So let's say one farm receives 100 ton of organic waste per day, 3 truck and trailer units, and we're taking out 1 truck and trailer unit of vermicast every day. So we mix it and we put it out on farmland in those windrows. So you can assume 3,000, 4,000 tons per hectare, which is, if you would tell this someone from the Landwirtschaftskammer, Untere Wasserbehörde in Germany, they would just go, oh my God, how can we do this? So much nitrogen on the ground. But actually we are measuring it and we're just there for 1 year. So we put it out, it takes 1 vegetation period, and then we harvest the vermicast. So it takes actually 1 year to break down. We can do it in 6 months' time, spring and summer. It takes a bit longer if it's autumn and winter. For organic certification, we need to do it 12 months. That's a bit of a crazy, even if it's done after 6 months. So it's not about the product, it's about regulations. And this is coming from the US, where they have continental climate, so it shuts down a bit in summer and winter. So they want to make sure it's processed, and rather than going for quality in the product, they go for time. But time is not the real best indicator. And then we pick it up, we leave like 2 millimeters of vermicast behind. All the remaining excess vermicast is reduced. So going back, so we have 80 centimeters of feedstock, we call it, for the worms, reducing it to, let's say, 15 centimeters. We take away 14.5 centimeters, leaving very little behind, which is incorporated, and then the next crop will grow, which we call catch crop. We're monitoring nitrogen and phosphate and heavy metals in the underlying topsoil. We never had an increase, because the next year we're on the next paddock. We are rotating like in a crop rotation. This is the advantage we can do. You would say this takes a lot of land. Actually, it doesn't. So we pay a lease to the farmer, so the farmer's not losing any money. Let's say between 1,000 and 2,000 New Zealand dollar per hectare a year. The farmer remains with 2 millimeter, 5 millimeter of vermicast, which is, again, the same money on top. So they don't have to pay for the soil conditioner. We are growing earthworms, so they have additional earthworms. Then they have the vermicast on their farm. If they want to spread more on their farm, they don't have any transportation costs, so they can utilize it on site. Now we have a new concept. We not have a centralized mixing area, and we are serving the farms surrounding us. So we're actually working with all the farmers, and we make sure every farmer gets sufficient vermicast in return for leasing their land for the revenue. That's how we integrate it in the farming. You can't see anything of this. We have our reception area, which is a concrete pad, and we have a container for our staff and machine. It's invisible, it's integrated. You have no big thermal composting plant which smells sometimes. You don't have these fungi, these domes, looking sometimes like, let's say, big investment, $30,000 for an anaerobic digester, which is sitting there for 30 years plus. And that's the beauty. Or we can say a disadvantage, because if you want to have someone supporting you and they want to show something to the people, let's say in government, you want to show things, but there's nothing you can see. So you are showing some invisible things, well-integrated things. Well, how do you show this on a camera? How do you show this on a poster? As you see, but an anaerobic digester looks great. You see, you can have these computer models. It looks fantastic. That's an advantage or disadvantage? I see it as an advantage.
And you have your agreement with the farmers around you, because I wanted to ask you, well, if you stay on one area for 1 year and then next year move to another one, you always have to organize upfront a farmer or 2 farmers in the 1, 2, 3 years ahead. Where can I go in 2022, 2023? But you have arrangements with the farmers around you.
It was very difficult in the beginning because farmers didn't believe in what we're doing. Also, region councils, which is the environmental authority, we did a lot of trials at the beginning, and They were very supportive. They are very supportive in New Zealand. They take care of the groundwater, Odour emission on the soil. So we are working with them to do ongoing trials. We monitor what's leaching out of the windrow potentially. But they're open-minded. They can see that we need to find solutions, and you can't just say, well, there is no formula, there's no template. You can't tick the box vermicomposting because it's new. So they're very innovative. And in the last couple of years, we can see there's a shift, there's some momentum. Farmers are contacting us. Can you run a worm farm at my site, please? How do we do this? Do we have some ways for in the region so we can set up a worm farm? This is why we believe, or we are convinced, we can double our capacity the next year. So we're employing more people, environmental managers, on-site managers, more staff. We do a lot of training on site, so we are ready to roll this out, ideally New Zealand-wide. And this is a game changer. So we can really do this, and we are combining all the time. We're doing new trials, looking at cardboard, looking at waste paper from fast food chains. We are looking at serving hotels now and hospitals. And the beauty here is they don't need to separate the food waste from their paper tissues, paper towels, from their serviettes, from their office paper. In theory, they can put it into one bin, or they can separate it with products, with these, you call it incinerators, with the biomaster. So you have a liquid one, which we can easily handle. It's very hygienic in the kitchen. We can suck it up. It's a liquid form, easy to mix in, again, with our paper towels and tissue paper at the worm farm. We can separate it at source, make sure it's clean. We can pick out all the plastics from the other waste stream, from the toilet, bathrooms, and the worms are eating it. Another advantage is if there's a piece of plastic, our employees, these 3-4 billion of earthworms working for us, they all have a brain. They're feeding around the plastic. Worm casting is less than 2 millimeter, like sand, and we can screen it out so the plastic remains on the screen. It's not like a thermal composting plant where plastic is melting and you have to shred it at the beginning. So we are not generating microplastic. We can screen it out, most of it. And that's another small advantage we figured out in the last years, once we've done those trials, taking on this food waste, which is often contaminated with plastic.
Very interesting. I think I see a lot of benefits here, but maybe let us try to get back to the question. We talked about time concerning the comparison of the three types. So you said you can do it in maybe 6 months, but in some areas you have to do it for 12 months. What about thermal composting and AD treatment? I think they're a little bit faster here.
Yeah, thermal composting, depending on the technology. So you can have an initial very fast processing in Trumbull, these hot rod systems, or Trumbull composting, or in enclosed chambers, containers, which is just several days or weeks, maybe up to months. It's continuous flow system, but you need to have a post-processing in windrows, usually enclosed, and you have to turn it. So probably in 3-4 months you have a stable compost, which is not reheating. A lot of plants actually releasing a pre-compost at an early stage, which is still getting hot, which technically is not a real compost. I'm not sure about anaerobic digesters, but it's a continuous flow system. So you can say it takes a year actually, because if you look at from receiving and distributing it to the farm, it takes a year. You have to store it until the next springtime. So you can do all the calculation that it only takes a few weeks. Actually, it doesn't, because you have the storage capacity you have to hold on. We have no infrastructure other than the reception area because we're operating on farmland. Time doesn't matter. We reimburse the farmer. It's a win for him. He makes money out of it in multiple ways, as I explained. It's a bit difficult to compare. If you would have for investment in a building, in a factory, in a plant, per square meter or per $1,000 investment, what's the turnover per ton per time in seconds? I think we would outperform any of the other ones because our capex and opex are so low. And I think that's probably a challenge for someone, the economic guys to figure out what are the true costs of this. Yeah.
Okay.
Interesting question, concept.
This was talking about time. I think we haven't talked. We talk about the three types: vermicomposting, warm farming, thermal composting, but the natural thermal composting and anaerobic digestion. We are not talking about these 24-hour composters coming from Asia, because I think they are in this category. They are more like drying machines, because with a lot of electrical energy you produce heat and you dry it. I think this is something completely different. So therefore, we are not talking about these types of. They call it composters. You could also call it drying machines. But I think this is completely different. To summarize the comparison, maybe the last point I come up with, maybe we forgot something, then please add it. But what about the influences from weather conditions, from maybe also depending, I think vermicomposting won't be able to do it in Siberia. When is it too cold? When is it too hot? What moisture is perfect? What is if it's raining for 3 weeks? What is are the worms dying? Are they draining?
I would say you can do vermicomposting everywhere where you find worms, earthworms on this planet. So if they are native earthworms, the environment for these species is okay. You won't have it on Antarctica. I think you don't have any worms in Siberia. I'm aware of. So this is where you have your limitations. You won't have any worms in a desert either. So these are the limitations probably. And it's probably temperature, moisture content. That's it, I think. In Central North Ireland here, we have rain for about 2,000 millimeter per year. This is 7 times as much as in Central Europe and Germany on average. The leach, from environmental point, the leaching risk is 3 times as high. So we are capable of doing so. We do have droughts sometimes. We had droughts for 3 months, no rain, and we're not irrigating. It didn't put us out of business. We are still operating. What it does, it takes longer. So I mentioned the windrows are up to 80 centimeters high. When it's getting dry or hot, the worms are going down. If it's getting cold, and we're operating in alpine climate as well, they're going down in winter. If it would freeze through, which you might have probably in northern part of Germany this winter, you would have to re-inoculate, or you trust on these worm eggs that they survive the frost, which they do, and then you have to start almost from scratch. You have to start again. This happens every now and then. So we have a drought, we have a very dry, a very wet condition. We have to adapt it, but the idea is working with nature. So we try to figure out how far can we go and what is a safe area we're operating in. So rather having a bit wider CN ratio than the optimum, which is 25, again this 20-25 for worm farming, let's take it beyond. And if you read the papers, worms can handle a CN ratio of 50. It's not the most economic in regards to speed if you would do it indoor, but it's the most economic if you do it outdoor. You can do it in many, many places. You just have to adapt the technology. Or you combine it with thermal composting. Have a fast thermal composting first, and then you have a process in worm farming afterwards. Eating the worms, once it's cooled down, the worms can digest most of it. Even with anaerobic digester, I mentioned the trial we're doing in Germany. Take the solids, the separated, the solids from the digestate, and see how we can add it to vermicomposting. It's difficult because of the high ammonia concentration, but we can do it. We manage it. We're taking a lot of anaerobic digested sludge from wastewater treatment plants. So sometimes it's combining it and finding the perfect fit for your environment, for your region, for your customers, for your end users. Vermicomposting is not a silver bullet, but it works in many areas where we are here. It will work in many areas in Europe if we wouldn't have the limitations from our regulations in Europe, because there is no, don't find a form for vermicomposting or Vererbung mit Regenwürmern. It's not a compost, so vermicompost is not in Realgütegemeinschaft. It doesn't fit because we are technically not doing composting. So we won't fit in their system. If they want to adapt it, it's just because they want to, but we don't need to. It's not required.
But concerning our comparison, did we miss anything or some major pros or cons for vermicomposting? Would you like to add something here where say here you are unique and we haven't talked about that?
I encourage every household, every single person, every school, kindergarten, your office, to start to have their own worm farm. It's first of all, it's fun. You find a lot of worm farms you can buy online in garden centers on our German website. You can find, it doesn't matter which type of worm farm you're actually buying. Get started with a cheap one, see what it does, how it works for you. And it's a good education purpose as well, because if you have a kindergarten at schools, you can train the next generation and make them aware of organic resources, that it's not a waste. It's a food for earthworms. You can see how they multiply, how actually you can see exponential growth in real with the worms. You're not just on the statistic on a virus, how this pandemic works out. You can have a worm pandemic in your worm farm. Unless you reach a maximum capacity, then they stop breeding actually. So it's not overflowing. It's fun. It takes the pressure off the community, less organic waste. You can use it for your potting mix. It's fabulous. And then when you like it, you can go more the advanced worm farms out there, which cost a bit more money, or you can find a local commercial worm farm taking your excess food waste, which you can't handle in your small worm farm in the office. But keep one for training your staff, raise the awareness. And I think that's great. Of course, a small worm farm has some limitations, so you don't want to feed meat, lots of breads, nothing with high acidity like lemons, oranges, or very spicy like garlic or some other spices. You can't feed bones and fish bones. Industrial scale, we can manage all this because we just blend it in at small ratios, and it's like some lemon juice on your salad. You let it is perfect, but a whole bucket full of lemon juice would just set up your stomach. See where I'm coming from? It again, size matters. So, and then you have to differentiate. If you don't know what a commercial worm farmer can take with vermicomposting operation, don't go to Google and see what they say. They would say you can't take onions, you can't take lemon or whatever. We can. Talk to us, the professionals. We advise you what can be taken and what not. We can take biosolids. The worms sanitizers, all the pathogens are gone. We know this. So talk to us rather than ask Google, Yahoo, and all the others.
Great to talk about the do's and don'ts. Maybe talking about science. We met in Valencia 6, 7, I don't know, years ago on a conference. You're going out on conferences telling people in the science community about it, and I think you already mentioned it, a lot of scientific papers. You alone, I think, published how many? 27. You can find on ResearchGate. How do you see scientific point of view of vermicomposting? Is there still a lot of research to be done, or is there already a lot of knowledge? And what is the science community thinking about it?
We actually have, it's probably almost an exponential growth in publication on this topic. It's about vermicomposting, the process. But what we can see more and more is how the benefits of vermicompost in agriculture, horticulture, viticulture, in potting mixes. And we're just starting to understand it. We can see the benefits. We can measure the yields. In some places, I mean, we did this at university, looked at mineral fertilizers, and we were excited. We got an increase of 2% increase in yield. I've been approached by farmers and really showed me yield increase of 20% on maize, on silage. There was a dry year, And I couldn't believe it. I said, must be something like 20% is unreal. So what have you done different? And he showed me. He has proven to me. I wasn't scientific. He had this one paddock with 2 millimeter worm casting and the other without. And we were digging holes and we could see a difference in the root growth. And if you think about this, this is so exciting. You don't have this with compost. You don't have, definitely not with anaerobic digestate. You don't have this with urea. Vermicomposting is triggering root development. So if a plant is growing more roots, what does it mean to the ecosystem? First of all, deeper roots, the plant can access more water. And this is probably what caused it. It's like a natural irrigation or water management system. Then we have nutrients which are not mobile in the soil, like phosphate. So the plant's reaching out to all these phosphate fertilizers, so the farmers actually saving on buying in fertilizer. They can unlock these fertilizers in their soil. Deeper root system means we prevent nitrogen, nitrate from washing out of the root zone, beyond the root zone, meaning it's going to the groundwater. If you have deeper roots, it takes longer for the nitrogen to bypass the root system, or the plant has more time to pick up the nitrogen, grow more roots, and grow more fodder or food or fiber or energy plants. And this is what we want, and this is what we are lacking. Less organic matter means shallow root system, means higher risk of nitrogen leaching. And this is what I got aware of from drinking water catchment operators. They are recognizing, because they often have no animals in these regions, that the organic matter in the soil is decaying, and that's where we started originally. Here the vermicast can actually grow roots and mitigate these nitrogen losses. And by growing more roots, what is the plant doing? It takes CO2 from the atmosphere, turns it into organic matter, puts it into the soil. This is called carbon sequestration. So we can do whatever we want. Why not leaving it to nature to sequester carbon for us? We just have to encourage nature. So why is vermicast doing this? It's the bacteria in the guts, in the stomach of the worms. They produce the wider term part of humic acid. So it's gibberellixins, auxins. And these are the carrier, these are the transcript, telling, communicating between microorganism in the soil and the plant. So somehow the microorganism wants the plants to grow more roots and put sugar into the soil for them to feed on. At the same time, the plants want nutrients from the soil to grow fruits and seeds and to grow above soil. And so the plant is very economic. It doesn't grow roots if there is no demand. If you're feeding it on top with mineral fertilizer, you can see less and less roots are growing. As a result, less food for the organism, less organism in the soil, less organic matter. And we spoke about this. As soon as we get organism and they tell the plant, hey, we're here, please grow roots, give us sugar, give us some part of the photosynthesis because it's dark down here. Therefore, we give you micronutrients. We provide everything. We unlock phosphate with enzymes. The whole thing works. And this has been developed over the last 600 million years. We didn't forget about this. We didn't pay enough attention. And there comes the science in. When you look at universities and research institutes, we rely on funding from taxpayers, from the government, as well as from industries. So which industry do you believe has more funds available? Is it the mineral fertilizer industry, or is it a worm farmer like us? So who can put money into research institutes? So somehow we have to ask our governments and agriculture and universities to say, hey, this is so interesting. We actually should spend a little bit of money. And it doesn't need to be either or. I think if we have a healthy soil, this healthy soil can actually grow to the potential by combining mineral fertilizer, farm effluent, farm manure, digestate from anaerobic digesters, and vermicompost. So the combination, I think this is the golden path. Some of these solutions won't work for organic certified. We all understand this. But I think there's a golden path which we can follow and which I can see. This is my vision, which is motivating me. So it's working together on the goal to improve our soil fertility, and this will fix a lot of problems, not just the organic waste, but also carbon sequestration, the climate. And again, we have healthier food, less chemicals we need. Yeah, I love it. It's my passion.
You mentioned the carbon sequestration. I think these CO2 certificates, they're coming up again, I think, which is good, yeah, because therefore more and more companies get motivated in trying to save and CO2 on one hand, and then give it back to the earth, yeah, like you're doing it. You say you're storing it, you're in the soil. Have you thought about trying to get the certification for your process, that you get also money for the CO2 credits, more or less? Therefore, you would need a life cycle assessment. I assume when there are thousands of publications already on vermicomposting, there might be a lot of life cycle assessments already. Do you know about some, or have you done your own life cycle assessment?
I've read some papers on comparing vermicomposting and thermocomposting, but it all comes back to the individual technology. So most of the composting plants are very similar, but there are differences. Worm farming is in other places done different as in our place. We can't do it on our own. We don't have the resources because we've never received any funding. So all we're doing is paid by the industry producing the organic waste and by the farmers purchasing the product. I would need to employ a full-time scientist, which is a lot of money, and additional resources for references for none of this costs. We can't afford this in our business. We are just not set up for it. If I would have $1 million surplus, I would set up another worm farm. If that's more important rather than proving what I know is happening as well. We are very open. We would love to invite other people if it would be funded by someone else. We would we would love to open our books, having these people walking at the worm farm, taking all the notes, taking all the data, and verify it and compare it with other technologies out there. But it's really, if you have these startup companies, without any funding, you can't do it. You can't.
Getting the information out there, you mentioned, and I think talking about the media coverage, you did your TED talk. I also saw a lot of TED talks concerning black soldier flies, which is maybe a little bit a similar technology. And as soon as there is a startup doing either vermicomposting or producing warm composters for schools or families, they get a lot of media coverage, and I think it's not a hype maybe, but I think it's the right time at the moment. Do you see this as a benefit?
When there are new things out there, we pay a lot of attention. When we looked at renewable energies and anaerobic digesters, as a result, we have 10,000 of these digesters in Germany on its own. We're starting to put in the first decent ones in New Zealand now. I think, and the worm farms, there are 10,000 out there, small ones, but let's say probably just 20, 30 commercial ones at a larger scale, industrial scales, as we do it here in New Zealand. I like those people jumping on the running train, as long as they do it ethical. So first of all, they need to understand what they're doing, and they really need to educate themselves or get experts involved. Sometimes they read things, they I can do this, I just take some waste, chuck it on the land, put a handful of worms in and walk away. You can get it wrong. And this would do a lot of damage to the industry. So you have these anaerobic digesters with leakage. There are publications where you have 20% loss of methane from an anaerobic digester. If you would say, oh, they are polluting the environment, they are releasing more methane than generating, so this is all anaerobic digesters need to stop tomorrow. That's wrong. There are very good ones, and there are areas where they really make sense. And other areas, they don't make sense. Probably it was kind of, call it hype, call it, in the spirit, we believed in it. It also comes back to scientists like you and me. We need to be honest. And when I received my PhD, my doctor father spoke to me and said, Michael, you get this PhD title, and which is good. We honor that you have done all the research, but it gives you responsibility to the community who paid for your PhD, for your education. You have to be ethical to these people. So you have to be honest. You can't mislead those ones. So I try to do this as much as I can. Some things I don't tell from the business point. This is IP and I want to have the advantage developing it, even because I spend my own money on this. But other things, I'm honest. If I would do damage to the environment, I'm not doing it. And I often missing this with other competitors, with other people on the market. I don't see them as competitors. We're all in the same environment. We want to serve it, and there's a lot to do. There's more to do than any one of us can actually can do. So I'm not really under competition pressure, so to speak. I would like everyone to be honest. And if there is, for example, an anaerobic digester in an area where, first of all, you can't dispose, or it's very difficult to dispose the effluent, and you have to carry it another 200 kilometers. If there's no demand for the energy, because there's so much energy around, either geothermal, gas, whatever, there's no demand for the energy. So why putting it up there? If you have to carry it, lots of transportation to offset the benefit of an anaerobic digester, because an anaerobic digester doesn't take away the waste. It's just a processing on the way for beneficial utilization. The same with worm farming. You can't say, well, let's have a worm farm in Auckland, which has 2 million people. You can't. There's no space. So we have to acknowledge, well, if we bring in the food 200 kilometers, the cabbage and the vegetables and the fruits, we have to backload with the food waste to grow these foods. So we have to make some, have to make some commitments. Often the city says, well, the food waste is here, we can't allow to transport. All the transport costs back to the country. It just costs so much carbon dioxide. You have to build it in the equation. If you bring something in, you have to bring it back. It doesn't work. We have to redistribute. There was a scientist, Quintern, he has this Quintern circulars around a community 100 years ago. The city, and then you have the vegetable ones where all the biosolids went, where they grow the high demanding nutrients fruit, and then they had the cereal areas, and then they had the forest with all the animals in the forest. This has gone global. So the industrial countries, we are feeding at the Amazon. So that's where we get a lot of nutrients coming in. So we have to consider, if we have too much, we have to take it back to these soils. Do you want to cart digestate to the Amazon? Do you want to take compost to the Amazon? Or you want to have worm cast pellets to the Amazon? Yeah. That's another vision of mine. Sharing these excess of nutrients, of food we allocate in our industrial world and give it back to the developing countries where we gain a lot of natural resources. And I think that's another opportunity for the next generation to look at.
But you have mentioned it yourself. You have to do it right. You have to know what you're doing, even in vermicomposting. And therefore, maybe sometimes legislation helps. But to build a good legislation, which maybe also deals with vermicomposting, you need a lobby. And you said the mineral fertilizer industry has an enormous lobby. I am so sure about that. You maybe not yet. Are you trying to get there? How often are you talking to the government in New Zealand and maybe also in Europe that your process gets certified? You maybe your worm compost, your worm cast, maybe will never get a RAL certificate of a quality compost in Germany. But what do you think about that, the legal aspects?
Okay, first certification. In New Zealand, we have a standard for compost, potting mixes, mulches, vermicast, vermicompost. So we are meeting those standards. So we're kind of certified. So meeting those standards is important. We do all the tests. Some of our products are organic certified for international standards. So it's kind of certified. You can see meeting those standards. I don't want to be part of RAL because RAL is for a compost. We are not a compost. I'm not interested. They should concentrate on their compost, make sure they do their work on their compost, and make sure it's meeting those ones. And my concern is about, for example, biodegradable plastics in thermal composting. We need to understand this more seriously, and we need to look at this more honestly. I think there's a lot of things RAL need to do. That's for the German part of it. Speaking to environmental authorities throughout, at least New Zealand, Australia, Germany, and the Netherlands, regulation is a framework, and different countries have different approach, and it's part of the history, it's part of lobbying, of course, part of interest. It always comes back to the individual person we are dealing with, and if we are open, we are honest where the risks are, we can start negotiating and start looking at the risk. What monitoring do we need to do? What are we doing if something is going wrong? Do we put a bond in place to recover things? Is there an insurance company policy? What are you doing if it stops? So if an anaerobic digester failed, you have a $30 million plant sitting there. If we are failing, we just stop tomorrow. We sell the machineries, we're gone. We stop it. Never happens again. If we make a mistake, it's easy to adopt a worm farm. Anaerobic digester, $30 million plant. You want to make some adjustments, cost millions. We can upscale it. We can downscale it tomorrow if we want to. We can just stop. We can take twice as much on site as we want. Try this with an anaerobic digester. Half the capacity. How you want to do this? Double the capacity without adding another $30 million? You can't. So this is legislation, but it comes back to the people who are working with this. They are employed. They have a supervisor. They have to justify the decision that they are making on behalf of the institution, on behalf of the people, on behalf of legislation, of rules, of laws, of bylaws, whatever. So we have to work. What I would like to see is we have it in New Zealand. We get a limited permit for a year. That's how you start, and a lot of monitoring. And then you can extend it. And they have the right to override any rules, conditions we have in place now. If there's new findings, they can overrule it and can say, from tomorrow on, Michael, the CN ratio need to be different. From tomorrow on, you can only do this much. Or, Michael, it's cool. We have another problem here with a waste producer. Can you take care of him, please? Can you tell him what you're doing? Maybe it's a solution for her or him. And this is what I'm missing in some countries. Sometimes you could sell it, over-regulated, and there is no space to move. You have waste regulations, you have fertilizer regulations. The current situation, if a country has a problem with organic waste and water quality and soil quality, based on the current regulations, would it be fair to say these regulations are not fit for purpose? So we need to make some changes to the regulations. We can't wait for a solution that fits into this regulation, because what fits into the regulation at the moment is causing these problems. So we have to move. We have to change. We have to be open-minded. We do mistakes. Yes, we will do mistakes, and some mistakes will hurt. But we have to make sure we make mistakes fast, cheap, and easy to fix, instead of waiting for the silver bullet. Someone comes up and then, oh, how are we doing now? There's a worm farm in New Zealand. Can we adapt it to Germany? No, we can't. Not overnight. It takes 3, 4, 5 years. But I would like to work with someone. But often it feels like I'm wasting my air.
No, I think this was a great closing statement. Michael, I love talking to you. I love your passion. I think you're an outstanding pioneer, and don't give up. I wish you all the best. Hopefully we'll meet soon, maybe in New Zealand or in Europe. But please continue the great work you're doing, and I wish you all the best. Stay safe, stay healthy, and all the best with your business.
Thank you very much, Michael, for having me. You're a fabulous host. It was a pleasure to talk to you and for this discussion. It's almost 2 hours. I don't know how long we'll carry on. You might have to split this. Thanks to the audience holding out as long as you cut it, or maybe you split it. Whenever you get a chance and visit New Zealand, please bring your camera and we will walk around these worm farms and you can have a video and an on-site discussion if we want to. At some stage we can do this.
I will. I hope. I'm looking forward to it. Thank you very much.
Thank you, and thank you to the audience. Bye-bye.
Thank you. All three technologies have the same problem. Yeah? Waste on its own. Sorry. Waste on its